Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog.
Good evening. I'm Yvonne Stapp for Science for the Public, and welcome to Contemporary Science. Tonight, our topic is space weather, and our distinguished guest to explain why scientists are closely monitoring the sun's activity this year is Dr. Jeffrey Hughes. Dr. Hughes is a professor of astronomy and former chair of that department at Boston University, and he's the director for the Center for Integrated Space Weather Modeling, which is a National Science Foundation Science Technology Center. Dr. Hughes is an international expert on the dynamics of the Earth's magnetosphere and its interactions with the solar wind and the ionosphere, what's known as space weather. He received his Ph.D. in space physics in 1974 from the Imperial College, University of London, and he joined the astronomy department at Boston University in 1978 and was director of the Center for Space Physics from 1988 to 1997. Professor Hughes has chaired the National Science Foundation's Geospace Environment Modeling Steering Committee and served on prestigious committees for the American Geophysical Union and the American Institute of Physics. He served also as associate editor for the Journal of Geophysical Research. Although Dr. Hughes has a long list of professional publications and many distinguished associations, he also has a great reputation as a teacher and a communicator of his field, space weather. And he's a great advocate of making this field accessible to the general public. We are very privileged to welcome him tonight to Contemporary Science. Welcome, Dr. Hughes.
It's wonderful to be here.
Thank you. And we'll just break this out in several categories. You have some really good images to show us. So we'll start out by just talking about what space weather is, then talk about the solar cycles, then the Earth's magnetosphere, and then your research. So give us plenty of notice here of what's coming up. So first of all, what is space weather?
Well, space weather is a relatively new term because the way the sun behaves has started to affect us as a society much more in the last few decades as we become a much more technological society. Mm-hmm. So the sun's been doing more or less what it's been doing for the last 3 billion years or longer. But we as a society have changed. And as we put more spacecraft into space, with more miniature electronics on board, as we build new kinds of technology on Earth, as we become more dependent on wireless communication, both within Earth and Earth to space, what the sun does affects us. One example is, if we can look at the first slide. Yes. This is a picture of a microcircuit on a spacecraft. On the left-hand side, the circuit's been magnified almost 200 times, and there's a little speck pointed out by a red arrow. On the right-hand side, it's been magnified over 4,000 times, and you can see what that speck actually looks like. And that's because solar particles hit that circuit and damaged it. And as we make circuits ever more small, that kind of damage can completely change a circuit and actually completely disable an entire spacecraft. And so you can lose several $100 million worth of spacecraft by solar particles hitting it. Before we had spacecraft, that wasn't a problem. Yes. No one cared that there were particles in space. Right. The next picture is a transformer, part of the power grid. This one was, I think, somewhere in New Jersey. That burned out as a result of power surges, current surges in the grid caused by currents induced by magnetic variations caused by the sun. And those of you with a long enough memory will remember in 1989 there was a massive power outage right down the East Coast caused by a solar storm. And as we build more and more grids, long wires basically over the surface of the Earth, they're vulnerable to changes in the magnetic field causing circuits and doing things like this. So those are just two examples of what space weather can do that until we started building these technologies we were completely impervious to.
Right. So some of these storms are rather bad, I guess, but right now it makes everybody nervous because we are so dependent on electronics. That's our flaw. Space, air flight, everything, right, would be imperiled with this sort of thing. In terms of when we start space colonizing and travel to the moon and more for longer periods in Mars and so on, is this an issue then?
Very much so.
Okay.
If you can think back a picture to what happened to that electronic circuit, think what happens if a particle hits a piece of DNA. It can completely sever the DNA, and that's not good for the cell. Most cells, when that happens, learn to, the body kills that cell off and you're fine. But it's also what happens, eventually you can get cancer and eventually radiation sickness if you get a big enough dose. Near the Earth, we're protected by the Earth's magnetic field. So the danger in a place like Space Station, which is really only just above the atmosphere, is relatively mild. But if you venture far out into space, to the moon or further, then you're very susceptible to both cosmic rays coming from the galaxy and particles coming from the sun.
So this is not a wonderful combination, and they'll have to really take great precautions, I imagine, more than the sunscreen.
You need rather more than sunscreen, yes.
Good. Now, if you'll tell us about solar cycles. So we know there are these cycles, but we don't necessarily know a lot about solar maximums and solar minimums and these cycles that suddenly they're paying a lot of attention to. Could you tell us about this?
Certainly. The sun has sunspots. Galileo was the first to at least in the Western world, to notice the sun had sunspots, dark patches. They're actually caused by strong magnetic fields penetrating the sun's surface and causing that little bit of the sun to be cool or cooler. What's happened for the last roughly 400 years is that the number of sunspots grows and then declines on about a decade time scale, something like 11 years. It's to do with the way the magnetic fields are generated in the outer layers of the sun. And we're getting some idea of why it should be this quasi-periodic variation in the fields, but exactly what's controlling it is not well understood. This is a picture of the number of sunspots plotted over the last 13 years or so. It starts in the year 2000 and goes up to about the present, and then the red line is a guess. I can hardly call it more than that, of what might happen over the rest of this decade. So the curve was high in the early 2000s. 2000, 2001, we had a big solar maximum, lots of sunspots, and then over the course of the next several years, the number fell off, and we had what was the lowest solar minimum, few sunspots in 2008, 2009, that we've had in a century. And now we're coming up, getting into 2013 to the next maximum, but we're taken by surprise. It's not nearly as intense a maximum as we had a decade ago. The number of sunspots is less than half of what it was in the early 2000s. We don't know how to predict this.
So they don't know how to predict it despite the modeling because the sun has its own mind or whatever. Can you explain a little more about the dynamics within the sun that cause this kind of buildup that ends up with these, like the solar storms and the mass ejections?
Well, the sun generates its magnetic field by, now let me step back a little bit. The sun, of course, is generating lots of energy, most of which comes out as light and heat. The outer, roughly third of the sun is a little opaque, and so the light can't just shine through it. So the energy comes out by what we call convection. Basically, the fluid itself is moving around much like water in a boiling pot. Except it's not water, it's ionized hydrogen, and that will entrap and carry magnetic fields with it. And so this churning fluid basically wraps up any existing magnetic field and making it stronger. And that's the dynamo action that generates the solar magnetic field. The field is buoyant, so it will rise to the surface and burst out as sunspots, and then slowly disperse over the surface of the sun. And so over the course of this solar cycle, the field emerges and then moves over and calms down again and then starts building up again. But it's all to do with this dynamo action inside the sun.
And so this comes out as solar flares, and it comes out as coronal mass ejections. But are these the same things? Are they separate? Is there a relationship or anything?
Inside the sun, the magnetic field is basically just carried around by the fluid. But once you get outside, above the photosphere, above the surface of the sun that we can see, the magnetic field has more energy than the gas, and so takes control. And so the outer atmosphere of the sun, a region we call the corona, it's the magnetic field that governs the geometry, the shapes that we see there. That field can get wrapped up and twisted and occasionally rapidly readjusts and reconfigures itself. And when that happens, a lot of magnetic energy can get suddenly released. One of the things that happens is this feature we call a solar flare that have been observed for 100, 150 years, but we only really started to understand what they were, say, in the last 30 or 40 years, that it's this sudden release of magnetic energy that gives rise to in a real brightening of the sun in a very local area, X-rays, energetic particles. But that bit is retained at the sun. A coronal mass ejection is a quite different feature, where a piece of the solar atmosphere that's been held down by magnetic fields gets released and flies away from the sun. I can show you here. This is a picture of the sun, or actually the outer solar atmosphere, showing coronal mass ejections. The little white circle in the middle is a circle the size of the sun, but the sunlight itself has been blocked out by a disk that is several times the size of the sun, which is that circle in the middle of the picture. So what you're seeing, and I can make it run again, so the central disk is hiding the sun, and there's also this dark stripe down. That's an artifact of what's holding that disk in place. So that's not really part of the sun. But the rest, you're looking at faint light being reflected off the outer solar atmosphere. And this is a speeded up image taken from a spacecraft, a NASA spacecraft called SOHO, and you can see vast bursts of gas coming off from the sun, and realize that the size of the sun is that little white circle. These are massive bursts of gas coming out into planetary space. The ones we're seeing here aren't going to affect Earth because we're looking from Earth. But occasionally they come earthwards, and when those come earthwards, we can get a large magnetic storm here on Earth.
Okay. Now, when that happens, so the solar storm sort of stays there, it's these CMEs, the ejections that we have to worry about, correct? Does we're told now it takes about 8 minutes for the light from the sun to reach the Earth.
Yes.
How long does it take for these guys to reach? Should we run and hide right away? Or?
No, with these we get, depends how fast they're moving. Each one has its own speed, but anywhere from a day to 3 days.
Okay. So it's a little different from light.
Yes,
in
a
that
real fast
respect.
one gets to us in about a day.
Right.
And a slower moving one might take 2 to 3 days.
Okay. Now, I understand that we have satellites and things, we have equipment now to sort of watch, keep an eye on this stuff, and it's pretty awesome. But then, in addition to that, you have to try to predict what's going to happen. Is that appropriate to ask that here, where, like, when do we worry? So not all of those ejections, coronal mass ejections, will damage or threaten us, but I'm not sure, like, when they know when it might. So it might hit or it might not. In other words?
Yes, yes. There are many coronal mass ejections. Most of them don't come earthwards, so we're perfectly safe with those.
The other side, okay.
If they're heading off in the other direction, maybe if you lived on Mars and Mars is over there, you'd have to worry, but if you're on Earth, you don't have to worry. So a relatively small fraction head earthwards. We can see them leaving the sun, so that gives us some sense of how to predict their coming.
Okay.
By making measurements there and running through computer models, much like the weather outside.
Yes.
The weather forecasters use big numerical models to try and predict what will happen for a few days. We can do the same in space. But predicting how bad a geomagnetic or how large a geomagnetic storm is going to come from a particular coronal mass ejection is difficult. We don't really have a very good hand on that. Most magnetic storms don't cause very much damage. They happen all the time.
Yes.
It's a very few that give very large effects.
Right. I suppose this gets us into the magnetosphere,
It does.
and maybe you'll take it up there. So maybe that's the next question in that case. When it hits, it depends on this charge thing, right? Okay, so I'll ask that then. What about the magnetosphere, our savior out there?
Well, the Earth also has a magnetic field, which we've, again, known about for centuries, and mariners have used magnetic compasses to navigate for centuries. That also goes out into space and affords us protection. So let me show you a sketch. That's a rough sketch of what the magnetosphere is. If you look carefully where all those black lines are coming together, there's a small circle, half of which is white and half of which is black. That's the Earth, to scale. So this region of space, which is sort of sketched here, is the region of space where the Earth's magnetic field essentially holds sway and can deflect this, we call the solar wind, this gas coming from the sun, and it has to flow around. So the white area is the magnetosphere. The yellow area in this diagram is the region where the solar wind has been slowed and now has to flow around the magnetosphere. Because the Earth's magnetic field points in towards the North Magnetic Pole, how effective a coronal mass ejection hitting the front side of the magnetosphere is depends on the direction of its magnetic field. If the magnetic fields point in opposite directions, they can connect together, and that will couple a lot more of the energy in the solar wind into the magnetosphere and give us a large magnetic storm.
Okay.
And when the magnetic fields are pointing in the same direction, they don't connect so well, and the coronal mass ejection essentially flows around.
Okay. Does that mean positive, positive, negative, negative, no problem? But when it's positive, negative, this is
Yes,
bad times.
there's a rough analogy with, as you probably played with magnets as a child.
Exactly.
And
exactly.
put the poles one way, they'll repel each other,
Exactly.
put the poles the other way, and they'll attract each other.
So the magnetosphere works best if the incoming is, if you have the negative, negative, or positive, positive.
That's right, then they repel each other,
And that
essentially.
could be, is that a chance thing then?
Yes, as you mentioned before, within these coronal mass ejections, the magnetic field is usually coiled up.
Yes.
And so you're typically, over the course of one of these passing units, typically takes several hours to a day to pass the Earth, you'll get some northward pointing field and some southward pointing field. So you usually don't get off scot-free.
Yes, I see. So you're going to be biting your nails if it's a big one. Is that the idea?
But it's very hard. Magnetic fields, we can measure where we are, but it's very hard to measure a magnetic field remotely.
Aha.
And so we can't tell, even though we can see this coronal mass ejection coming towards us.
Yes, I see.
We can't tell what direction the field within it has.
Right, until
It actually
gets here.
Gets
Is that
here
it?
or gets to a spacecraft between us and the sun.
I see. So even though you have the Solar Dynamic Observatory, that really neat thing, and all of this monitoring equipment, they still don't know until it sort of arrives, or it's almost arriving.
Well, there have been a series of spacecraft essentially situated as sentinels in front of the Earth, but they're at a place where the solar wind passes about an hour before it reaches Earth. So that's not very much warning, but that's the warning we've got. We see these things about an hour before they get to us.
Right. There was an article recently about the concern, like space travel, everything is electronic, not space travel, air flight, everything is dependent on this. So it could really be very difficult, and people are trying to come up with apparently ways to safeguard planes in the air and so on. Now, if I recall, it mentioned something about software. I thought, well, it's still electronic, but I'm not absolutely sure. Are you aware, are there safeguards out there? Are they trying to do things?
Well, the biggest effect for airlines is planes taking polar routes.
Oh dear, yes, and many.
Because, yes, the polar traffic has increased dramatically over the last decade or so as Russian airspace opened up and people want to fly from North America to the Far East. If you get a significant solar storm, then particles from the sun have much easier access into the magnetic poles. And they can cause ionization in the ionosphere that blacks out high-frequency communications, HF radio. Now, normally, planes don't use HF radio. They use satellites, geostationary satellites to communicate to ground control. But if you get, the higher you go in latitude, if you're looking at a satellite over the equator, it gets closer and closer to your horizon. And when you get within about 10 degrees of the North Pole, you can't effectively communicate with satellites because you're basically looking at the horizon.
Yes.
And so they have to rely then on high-frequency HF radio.
I see.
And there's an FFA rule that a plane has to be in contact with the ground at all times.
Right, but it can't be.
And if it can't be, then it has to divert.
Aha.
And so most of the major airlines have become much more expert in space weather over the last decade.
I bet.
Yes.
Rapidly.
Rapidly.
Yes.
I've even had airline pilots come to my space weather summer school.
Oh, I see.
Yes.
I see. So you're training in right there. But I'm sure it's just causing all kinds of anxieties. We think naturally of the electric grid and whole cities going dark, or whole coastlines or whatever, But in fact, it's just massive, the kinds of things it will affect. So everybody needs to get out their candles for a while, and they do say that it could be a really bad one, as in like what is it that you talked about it once before, is the 1850s, it was during the Civil War.
Just before the Civil War, 1859.
Yes, that if we had one on that scale now, we'd really be in big trouble.
We would.
Because we don't have a way to repair these huge grids very rapidly.
Yes. What you're referring to is what's often referred to as the Carrington storm, because a solar scientist called Richard Carrington actually observed the flare. It was the first time somebody had actually observed a flare on the sun. And 18 hours later, this was a really fast-moving one, a magnetic storm started on Earth. The modern technology in 1859 was the telegraph system.
That's about it, yes, right.
But the telegraph system lays wires across the surface of the Earth, and these induced currents in those wires. Actually, fires broke out in telegraph stations with the ticker tape, and there's a wonderful recorded conversation between the telegraph operators in Boston and Portland, Maine, finding that because of these solar-induced currents in the circuit, it worked better disconnecting their batteries.
Oh, how about that?
Yes.
Makes sense, yes.
So they could use the solar currents to communicate.
Right.
So people have recently gone back and tried to piece together what happened. Aurora was seen in southern India and Venezuela and all sorts of places
way
like
down
that.
the East Coast.
Way down. It's hard. The data we have from that period is not what we'd like.
Of course.
But the feeling is that if that hit today, we would have big trouble with power grids over much of North America and Europe.
Right.
And power grids are, the power is transmitted as high voltage because you lose less energy that way. But then when you get to where you want to use it, you have to step down the voltage to something that can come out of the wall. You need big transformers. And those transformers are vulnerable. They're big purpose-built pieces of equipment. Some of them are the size of a small house. And if one goes, you can't just sort of go down the road to
Can't run down to Walmart.
Walmart or Home Depot and buy a new one. They're basically all purpose-built and take a long time to build a replacement.
Right.
So we'd be without power or have compromised power grids for a long time.
Right. So I hope that these governments around the world are paying attention to your kinds of research, right?
It's, yes,
they
have suddenly started to really wake up.
Good show in this year, good, very good.
Actually, there was last May, President Obama visited London. And he and the Prime Minister issued a joint resume that there would be joint work between Britain and the US on space weather. It rose to that level that it actually came out in one of their communiques.
Let's do hope that they'll keep it up, because that would be really catastrophic, obviously. But before, I'd like to go on now to your own research around this. Do you have any images for us about like the magnetic fields on the sun, or anything else that you want to show us, or shall we go on?
I did have a movie of a solar flare.
Yes, would love to see it.
So this is just looking at a small region of the sun, and you can see these loops are actually, you're picturing the magnetic field. You can't see field, but what you're seeing is the hot gas constrained on those fields. So it actually helps us picture the field. This loop is a few hours long, but that's actually what happens to a flare on the solar surface when a flare goes off, this large amount of energy.
And this we see particularly in these maximum cycles. Is that it, that we see that
yes.
more frequently or higher
Flares can
level?
happen at any time, but the frequency goes up during solar maximum.
A lot, and then people start to pay attention to it.
Right.
But it doesn't necessarily mean that it will be followed by a coronal mass ejection. Is that it? But they start paying more attention to it.
Yes, there's a close connection between flares and coronal mass ejections, but they don't happen one for one.
Okay.
If you get a large flare, there almost inevitably will be a coronal mass ejection.
Okay.
But there are many smaller flares that don't release.
Okay, I'll keep that in mind as I watch the sun, right? Okay. I'd like to turn now to your research. You have a long history with this, and sort of were in on a lot of the basics, I think, right? I mean, you know, as things were getting started, you mentioned earlier that when you got started, this was sort of a peripheral kind of a thing. It was a fun thing, and now it's very serious. So if you would give us some idea of how you work.
In many ways, what I do is began with the space age, and so I wasn't there quite at the beginning. When Sputnik went up, I was in elementary school.
I understand, but I meant in this, yeah.
But I was in graduate school in the very early 1970s, and so certainly know the generation of scientists who put up the first spacecraft. But at that time, what we were doing was pure science. It was fascinating, interesting, but didn't have any real practical applications. That's slowly come into changed over right. My career.
Yes. Did you expect it? Did you anticipate it when you were starting out?
Not at all.
You said it was esoteric at the time and it was fun.
And it was fun.
You had no idea it was going to be.
I think most scientists do it because they enjoy doing it.
Yes, sure. But you didn't anticipate that it was going to be front and center, as it certainly is now, and will continue to be with space exploration and so on. So what is it that you do?
Well, for the last 10 years or so, I've been running a large group effort. As I mentioned a while back, with trying to forecast ordinary weather.
As we all know from last week.
But the meteorologists are doing an awful lot better than they did 10 or 20 years ago.
Right. Yes.
And the reason they're doing better is because they've improved computational models. Computers have improved, and their ability to do this modeling has improved, so that now they can give us reasonably good forecasts several days in advance.
That's right. Yeah.
And so the meteorologists have started doing that in the mid-50s, and they've been doing it for about 50 years and got very good at it. For space weather, we basically decided in around about 2000 we'd better be doing the same for space weather. So I was running a large group spread amongst several universities and other research institutes, where we were trying to take models that had originally been developed primarily for scientific research purposes, to try and figure out why the sun did certain things, or how fields worked in interplanetary space or the magnetosphere, and build them into a suite of models that would help us predict forecast space weather. There were about 80 people involved in this, so it was big science in that sense. And much of my job was trying to keep people on track and keep people focused so that we could make progress, rather than
preventing war from these.
Yes.
In a word. Ego war.
Yes. And scientists are very independent sort of people. That's why they go into that. They do what they like to do. And so to get scientists to work as a team collectively can sometimes be a challenge.
I'm sure, right. Now, in working with these teams, you say team, so much of science like this today is so complex that you're talking almost about an intellectual organism. Different skills are put together. People have different backgrounds, and you have to somehow mesh that to make this kind of a program. Is that true?
Oh, absolutely.
First of all.
Yes.
And can you give us an idea of what kinds of backgrounds are we talking about that get involved in this when you deal with these huge teams?
It's like any team effort. It doesn't have to be science. You need a variety of skills to make some project work.
Yeah.
In this particular case, we need people who understand the computational sides of it, and how the computers work and how to make them work efficiently. People who understand the observations and how to make the observations and interpret them. People who understand the basic physics behind some of these processes and how to incorporate them into the models. And people who understand about computer visualization and can get the results out of the models that we can understand them. And you need all these different kinds of people working together to make a project like this work.
So it's like a physics and engineering and computational people and some
And
of
at the same time, we're trying to train the next generation of students.
Right. What is that like now? That must be an interesting field for somebody to go into. And
Oh yes, it always has been.
I'm sorry, yes, obviously.
But perhaps a little more, got more practical aspects now.
Yes, right.
But the way science is done has changed so much too. I mean, when I was a graduate student, science was done by two or three people maximum in collaboration, and now it's done in such more massive teams.
Right. Sometimes huge teams, and that must be difficult for everybody, because it's hard to form communities.
It's a different set of skills.
I'm sure, right, personality skills or something. What about the future of this kind of research? Where do you see this going?
Well, from a purely scientific point of view, what we can learn from our own neighborhood in space is how magnetic fields and matter interact, and better understand how this happens in the rest of the universe, in our own galaxy and other galaxies, in the space between galaxies. We have this great advantage: we can actually get there with spacecraft and measure things, whereas the astrophysicists are sort of hampered. All they can do is look at things from afar and try and piece together the evidence they can collect from the light and other radiation that comes. So we can gain this understanding that can help them interpret their observations. And that's what I see one as the most exciting way forward. Those more interested in the practical aspects, we're a long, long way away from, say, where the hurricane meteorologists are in being able to tell you where a hurricane's going to go over the next week. We have a long way to go in terms of building our models and trying to put all the physics into understanding these complex systems.
Right. And on that complex system issue, when we were talking before, you mentioned that there is a trend now, and of course it's very noticeable, about dealing with these kinds of phenomena in a rather different way. Would you go through that again, from breaking it down to dealing with this complex?
Well, it's perhaps a simplistic way of looking at it, but I think in the 20th century what science did was take things apart and try and figure out the basic structure of everything, whether it's taking an atom apart, whether it's understanding what DNA is. We basically took everything apart and understood what the pieces are. And I see our way forward now we understand how the individual bits work, is putting all the bits back together and understanding how the systems work. Whether we're trying to understand how the sun works, or we're trying to understand how a living cell works, or if we take billions of cells and make an organism and how the whole organism works. If you try to go from the molecular level up to the organism level in biology, you've got an awfully complex system of systems.
Exactly. Even a cell is extremely complex, and you need to know how it functions as a whole, and that's what you're saying about this field, the space weather, I suppose.
It's very similar. We understand reasonably well the individual processes involved, but then putting all those together so that they interact is a significant challenge. Let me give an analogy from terrestrial weather, ordinary weather. Nobody needs convincing that clouds are an important part of weather. If you build a typical meteorological weather model, you're modeling either a significant region like a continental-sized space or even the whole globe. So you have a grid of points. You're solving things on a scale of at least the size of a city miles. What goes in, the processes that go on inside a cloud happen at the scale of a water droplet. What makes a cloud form is water droplets forming. There is no way to put the physics of cloud formation and cloud physics in these other models because they're working on a completely different scale. So you have to take a model of clouds and simplify it and put it in these other models because the processes that go on clouds, and whether they reflect the sunlight or bring moisture and all that, is critically important to understanding what the weather's going to be.
Exactly.
So you've got these different systems you have to
Right.
build together and put into a model.
Right. So putting the systems collectively into something, so it's just not just the pieces, the components into a thing, an entity, but to continue the systems vis-a-vis other systems as well, correct? To make it understand. We're
Different
getting
spheres
better at it, but
interact, yes.
it's a very complicated process. That must be very interesting to be in the middle of that. Now, another thing you were telling me about was the archiving of data. It's practically a science. I think that in the general public, we're probably not, that part is sort of kept away, you know, but it's really quite interesting, isn't it? So we're not talking clay tablets that we can handily look at 2,000 years from now. Tell us about that, would you please?
Well, this is a challenge I don't think we've really understood yet how to face, but we can now generate so much data. Mm-hmm. What do you do with it? You brought up Solar Dynamics Observer, SDO, which was a wonderful new spacecraft launched a couple of years ago, taking wonderful close-up images of the sun, big telescopes. Each one of those images is, I forget, hundreds of megabytes, and they're taken, you know, many times a second.
Yeah.
And so you generate vast quantities of data, which has two problems. How do you store it? Mm-hmm. And how do you analyze it? Mm. And a problem facing all fields of science, and other fields too, is learning how to really get into these vast data sets and learn what's important in them.
Would you say that was just hugely different maybe from the time of Galileo? In other words,
it was hugely different from when I was a graduate student, let alone going back to
yes. It's actually, the problem is accelerating in a way. Is that, I mean, it's getting more complicated as the technology gets better, is that it, and can get you more data, but then you have to get an army of people to decipher it or figure out what's worthwhile or something.
We had a talk last week at Boston University by a scientist involved with the Voyager spacecraft, which you may remember now leaving the solar system. But they were launched in the late 70s. The memory capabilities of those spacecraft was a few kilobytes.
Oh, really?
Yes.
I didn't realize.
That was their entire memory.
It's so quaint. That's really.
Yes.
I can't even think of anything else with a few kilobytes of memory now.
Right. But it was a lot of memory back then.
So that's something. Yes. And your problem is that you're getting this just constantly, and lots of areas in astrophysics, they have just this reams and reams of data, and nobody knows, I guess, how to preserve it. Do you see this as being vulnerable down the line? I mean, the way that we store this kind of data has to be different from, really, even a generation ago, file cabinets and whatnot, right? With
no experience, because we've only had this kind of data for a couple of decades at most.
Yes.
We've stored data, as you brought up, clay tablets. Well, they probably went out a couple of thousand years ago,
right,
but we've used paper for a long time.
Yes,
and,
right.
You know, paper does age, but we can read manuscripts that are many hundreds of years old, so that works. We don't know how electronic data will survive, or what we'll have to do to keep it for decades or centuries. We haven't had to do it yet.
Exactly. And there's so much of it, but it's also very vulnerable to.
Is data stored from, let's say, the 70s and 80s, when the high technology was a magnetic tape. That's most of that is gone, unless people have read it. And even if you have a tape, can you find a tape recorder, tape reader anymore?
The equipment to read it, right? When future generations look back here, they're going to have a hard time maybe reconstructing all this information that we have accumulated.
Right.
compared
But we
to...
can go to a library and read a book that was written a
Well,
few
that's, I
hundred
was
years
going to
ago.
say we could go to some ancient monastery and dig out the old parchment stuff with the bookworms and everything. You could still make sense of these things, but this is just changing radically. More of it, but in a sense more vulnerable, perhaps, or vulnerable in a very different way.
Yes.
Well,
yes.
it's all very interesting. Is there anything that you would like to bring up in addition here?
I don't think so. We've covered an awful lot of ground.
I hope so. But in any case, what we'll do is say thank you for now and let the audience ask questions, and we will record them as well as we can here. Thank you very much, Dr. Hughes.
You're very welcome.
Okay.
Remember about magnetism is Velikovsky in the 50s arguing that magnetism would be one of the most important contributors to astronomy. And he was poo-pooed, he was ridiculed. And now, of course, you're mentioning that it is totally important. It's perhaps the most important phenomenon in all of astronomy. Would you care to comment?
I think that statement made 50 years ago was very insightful. Magnetic fields, unlike electrical charges, which come in two signs and so can cancel each other out, magnetic fields only come in one type, and so they can't. And so they do pervade the volume of space, and in much of space have as much energy in the fields as there is in matter. And so I think astrophysicists are only really starting to come to terms with what the role magnetism has played in everything from star formation to galaxy formation to...
And that's been only in the last 50 years or so. Mm-hmm. What the next 50 years will be like, God and maybe you know, but that's another.
I certainly don't. I won't comment on God.
This is perhaps a fundamental question that I've never been able to understand. From the sun's point of view, does it rotate? And if it does rotate, is there an axis of rotation?
Yes, the sun rotates.
The sun rotates.
It rotates with a period of about 27 days.
Okay.
And yes, it has two poles and an equator like any rotating
Just
body
like
does.
Okay.
The equator of the sun is very close to the plane of the planets because it's all one system. So the planets are all orbiting in the equatorial plane of the sun, more or less. The sun is fluid, and so it doesn't rotate as a solid body any more than our own atmosphere rotates all at exactly the same speed as the solid part of the Earth. And so different parts of the sun rotate at slightly different speeds. One can think of that as winds, if you like. Mm-hmm. But at the surface of the sun, the equator rotates significantly faster than near the poles.
Okay. In regards to this with the sun, over at Harvard, we saw a picture of the sun, and we saw two sunspots. And in time, we saw them converge.
Mm-hmm.
Now, if you deal with just, say, currents, opposite currents and so forth, and you're going to have attraction, okay? But what causes the attraction of two sunspots? That's it.
Well, the sunspots are regions of strong magnetic field. They usually come in pairs of opposite polarity. So one sunspot, the magnetic field is, if you like, coming out of the sun, and in the other it loops around and goes back into it. How the spots move is governed as much by the motions of the solar gas as it is by the fields. Because in the surface of the sun, the magnetic field is weak compared to the pressures in the gas. And so most of the motion in the surface of the sun, which moves the sunspots, is caused not by the fields, but by the convection of the gas.
Of that, yeah.
Yeah.
Thank you.
I recall reading that the outer surface of the sun is hotter than the interior. Did I read it correctly? Is that true?
Yes, in the sense the coolest part of the sun is just above the photosphere, the region of the sun where most of the sunlight comes from. The surface of the sun has a temperature in Celsius or in Kelvin of just under 6,000 degrees, and it cools down to about 4,500 degrees, and then above that the temperature rises rapidly, and in the outer region of the sun, outer atmosphere, the corona, the temperature is a couple of million degrees, which seems to defy any normal thermodynamics, that the energy is coming out, it should always go from hotter to cooler. It's the magnetic field that heats that up. The energy transfer is not thermodynamic, it's electromagnetic. And the outer part of the sun, the corona, is heated up by this magnetic energy propagating out and being released there and heating the gas. It's not as hot as the core of the sun, but it's significantly hotter than the outer layers of the sun.
Perhaps what we read. Thank you.
Yeah.
I have a question in that you talked about your research very generally. Could you define it, take a very specific thing that you're currently working on?
Well, one of the problems we're trying to understand with a postdoc working with me and myself is, can we really understand where different types of solar wind originate on the sun? Connecting what we see close to Earth, where we can measure it with a spacecraft, and where it's come from on the sun is not trivial. And by a combination of looking at the composition of the solar wind, which is 95% hydrogen, and most of the rest is helium, but there's small amounts of other elements there, because the sun has got all the elements in them, and looking at those elements and the concentrations of them, and trying to trace this, the where it's come from in terms of models of the solar wind for that particular time. We're figuring out that different kinds of solar wind might come from regions of the sun where it's completely open, right? In that it's easy for the gas to escape, and others where it's coming from loop-type regions, which we call the streamer belt, where it's much harder for the gas to escape from. So that's one of the problems we're looking at now. Much of my work involves both trying to interpret what you can understand from modeling these phenomena, combining that with observations, and by putting the two together, getting insight.
I had one other question, and maybe this is looking way long term from now, but you talk about damage to circuits when you've got vehicles up in space and so forth. Why not think about, can we duplicate the Earth's magnetic field, if you want to call it that, and create around the spacecraft a magnetic field which, when the particles come in, they will create ions and so forth. They will sweep from the North Pole to the South Pole and back again, and also in rotation. So is that a long-term idea, perhaps?
Shields up, in other words.
Shields up. Yes. No, it's certainly an idea that's been put around. The scale, just the length scales you would need that field to be, are, as you suggested, on the scale of the Earth's magnetic field. So in any foreseeable future, the energies and resources you would need to generate such a field in space seem completely implausible. Now, what happens centuries from now, I don't know. But with current technologies, generating a magnetic field that would act as a shield in space for cosmic rays and solar particles is not practical.
How many gigawatts of power would you need?
I don't know that's yes. But spacecraft work on watts and milliwatts and not gigawatts.
I have a very naive question. You were talking about early on in almost colonial days, they had this incredible flare. Supposing you observed that, just because you're observing all the time, and you had this 2 to 3 day window, what could you do about it? Anything?
Yes. The safest way to do to protect any technology is switch it off. Exactly.
Was that
Yes.
something that's practical?
I don't expect most people would say, let's have a human-made power outage for the next 24 hours.
That doesn't sound unreasonable compared to the consequences of burning half the power stations.
Right. I don't, it's not my job to run power grids. But the people who do run power grids are aware of these problems and now take more precautions than they would have done 20 years ago before these were properly as well understood as they are now. But they are also under enormous commercial financial pressures. And so I'm glad I don't run electric power grids.
Talking about this accumulation of large amounts of data, I'd just like to go back a little bit. If you look at the engineers which are doing research in various areas, in particular in our areas, high power microwaves and so forth in there, the national laboratories are developing huge codes in order to design a magnetron, a microwave device, magnetron. The people that are doing it don't know anything about the history of the magnetron. They don't care about the history. All they want to do is run the computer, okay? My experience from Raytheon, when an engineer came in and he was using codes, he did not understand the code, he does not test the code, okay? And he just runs it, and he gets, oh, look at this nice curve. Oh, isn't that wonderful? But he knows nothing about what he's doing. And from the engineering point of view of days before, it's your intuition which drives you into certain areas. You know that, oh, this is going to be wrong, this is going to be right, and you don't need the computer in order to tell you that and to use that to design, then you use that to design your device and so forth. And so this generation of all of this code and so forth, how much of it is going to be really useful? Maybe a lot of it is not really good data. Just a concern that I've got.
Well, we've got data generated by computer models, and we've got other observational data. We have vast amounts of data, or whatever it is. But you're bringing up another issue, that computer models are a tool like any other. And we have to learn to use them and not rely on them any more than we rely on any other tool and understand their fallacies. And you're absolutely right. Too much faith can be put into tools that are not well understood. Everything needs to be carefully verified and tested. Okay. And ultimately, it's intuition that does help. Yeah. But as problems get more complex, we can't do it with paper and pencil anymore either.
Unfortunately, but you're right.
Yeah.
Unfortunately, we have to stop there. They start kicking us out about this time. But I want to thank you very much again. Thank you also for very good questions. Thank you very much.
Thank you. It's been fun being here.